So let's talk about free body diagrams. As I introduced before, a free body diagram is a way to visually see all the forces that are acting on each object in the problem that you're trying to solve. So let me talk about how we draw these diagrams conventionally. You don't have to necessarily exactly follow everything that I say here, but these are kind of the best practices for having clear diagrams that will not lead you astray. So first of all, you draw a basic, very simple schematic of the object that you're drawing the diagram of. I usually like to just draw it as like a square or a circle. Some people like to even just use a dot to represent the object. So there's my object, okay? Doesn't really matter what it is at this point. This could be, you know, the problem I was solving earlier where I had like pushing around this cube or something like that, okay? Let me actually make it a little bit bigger since we're featuring free body diagrams in this video. Let's make a nice big square. Okay, there's the object. So I have in my mind, I know what object this square represents. Now I go through and think, what are all the forces acting on this cube? You know, like when I was pushing it across the table surface, I was pushing it with my finger. So you include that push of the finger in the free body diagram. So I would include, you know, I'm not sure which way this is for you because the video is mirrored, but I include, like, let's say I have this here. So a couple things to notice here. Normally the way we do it is we draw these force vectors starting from the center of the diagram, because it's nice to have a coordinate system at the center of the diagram here that all the vectors are coming from a common origin. And let me see, why is my line so thin here? Let's see if I can increase the thickness so that we can get some better looking vectors. There. Okay, so let's say we've got that. That represents the force of my finger. So again, I draw it starting from the center of the diagram, and I must get it pointing in the right direction, because a lot of the point of the diagram here is making sure that you can see which direction all these forces point in. You don't have to think about any equations right now. You don't have to think about any numbers. You don't have to think about really any like deep principles, except which way is this force pushing or pulling the object. Okay, so the finger is pushing it, let's say, in that direction. And you probably want to label this in some fashion. So maybe you label this as F finger. Okay. So I know what force that represents. You know, now I think to myself, okay, what were the other forces acting on the object? So maybe like in this problem that I'm using it as an example, maybe you say like, okay, gravity is pulling the object downwards. So I put a force that's downwards there. And this is the force of gravity, say Fg. And then maybe I say, okay, well, if gravity is pulling the object downwards, why isn't it falling? Why is it stationary? And the answer is because it's sitting on the table. So the table must be holding the object upwards. So we have an upwards force, and this is F of the table, let's say Ft. And then we talked about how there was significant friction between the block and the table. So we should include the friction. So I might have to think for a second, well, which way is the friction force going to go? Well, it's probably the finger is pushing it in one direction, so the friction is probably going to be in the opposite direction like this. So here's the force of friction. And then we start to get a picture, literally and figuratively, of what's going on in this problem. And then once you've written down all the forces that are acting on the object, then you can say, okay, my free body diagram is done, and now I can actually try to solve the problem. Let me make up a different diagram just to give you something a little bit juicier to think about. Okay, so let's say we had an object like this, and let's say maybe there's a force acting on it like that, and there's a force acting on it like this, and there's a force acting on it up this way. Okay, and when I do this, I would need to make sure that I know what the angles of these forces are as well. So I would want to label, you know, okay, maybe I know that this is a 30-degree angle here, and maybe I know that this here is a 40-degree angle or something. And maybe these are, in this case, maybe it's just F1, F2, F3. So like there's another example of a free body diagram. Now, the one point I want to make, and this is a point where you might go this whole physics course without ever realizing this, but if you do realize it, it makes the problem so much easier, and the procedure I'm outlining will make so much more sense. Once you draw the diagram, you're practically done. The diagram, a lot of students resist trying to draw these diagrams. We're not trying to make you like, give you some like dumbed down kindergarten problem where you're like coloring or something. No, this is actually like, if you stop a real genius physicist and you ask him to solve one of these problems, he will draw this diagram first, because you need this diagram to solve the problem. And once you've drawn a good diagram, the problem is almost solved, because all the information I need practically is in that diagram already. Like, you might want to approach this course as being very mathematical, and it is, but the math can all be seen in these diagrams and pictures, which is the whole beauty of why we draw them. Like, for instance, here, I can see I have 3 forces acting on the object. I can see what directions they point in. If you kind of start to think about the geometrical vector addition stuff we talked about, you can probably roughly say already what the direction of the object's acceleration is going to be, because you could visually add these 3 vectors to each other. You can also see how the F equals ma equations are going to shape up. So for instance, I can see, without even doing any numbers or any equations or anything, I can see, for instance, that like in the x direction, F1 is going to have a positive, and F3 is going to have a negative, and F2 doesn't have any x component because it's pointed just in y direction. In the y direction, I'm going to have F1 is positive, and F3 is also positive, but F2 is negative. So I can see that when I sum the forces, in the x direction, it's going to be something like F1 cosine 30 minus F3 sine of 40 equals max. And then in the y direction, I'm going to have F3 cosine 40 plus F1 sine of 30 minus F2 is may. The F equals ma equations would look something like that. But I can see all of these terms that are here. I can see right away, just visually, that I could predict that all of these terms are going to be here just from looking at the diagram. So if you can accept the fact of drawing these diagrams and letting the diagram guide you through the problems will be significantly easier, and you will not get lost in the weeds of thinking about this as being math, like a math class. You can actually start to understand what you're doing in these problems. diagrams. That's one of the real key kind of tips to actually doing these problems properly and really understanding what you're doing in the course.